the morning session with a talk by Bennetts, who's going to tell us about modelling water waves, overwash and ice.
Thanks, John. In the first workshop, there was, I noted a lot of talk about this new concept that sea ice is made up of floes. And I spent most of that time thinking, hang on, in the wave ice community, we've been doing that for about at least the 10 years that I've been around for. So the net result of that is that I'm now advertising my work as wave flow interactions rather than wave ice interactions. So that's where that's come from. Now I'm going to be speaking about just one specific phenomenon associated with wave flow interactions, and it's something that we call overwash. I'm essentially going to be presenting the PhD thesis of David Skeen, that suspicious looking chap you can see on the left there. But he's been a really good student and really driven his PhD himself. And I can undoubtedly say that he is the world expert in overwash, basically by default, because he's the first and only person to study it during his PhD. We've been supported by a team though, including Mike Malin, who most of you probably already know. Then there's Alessandro Toffoli and his student Filippo Nelli in Melbourne. They've helped us out on lab experiments. And finally, we've had Kevin Mackey's team at Michigan helping out on CFD modelling. The most important quantity in wave flow interactions is the ratio between the wavelength and the flow length. And throughout this talk, I'm going to be assuming that that ratio is order 1. That puts us in the marginal ice zone, but it means that we're not in the pancake ice region of the marginal ice zone. And it's what I refer to as the scattering regime, in which the waves force motion of the flows, and in turn, the flows affect the motion of the surrounding wave field. In this regime, the elastic response of the flows to the waves is of debatable importance. Typically in the models that I show you today, I'll be including the elastic response, but sometimes I'll drop it out, and I'm not going to make any further reference to it during this talk. I'm also assuming that the wave steepness Ka is small, which means we have linear waves, but I'm going to use those linear waves to force a non-linear response in their interaction with the flows. The schematic on this slide illustrates the standard model of wave interactions with a flow. I've taken this schematic from Vernon's 1995 annual review paper to make some sort of comment about how long this model has been around for. In the model, the water motion is modelled using linear potential flow theory, and the flow is modelled as a thin floating elastic plate. What you're seeing here is a schematic of the 2D problem, and I'll be focusing on that problem today. But we can also go to the 3D problem, it's just some extra computational expense. The problem is forced by a regular incident train of waves at some prescribed frequency, in this case coming from the left of the flow, propagating rightwards towards it. And the flow reflects a proportion of the incident energy back towards the incident waves, setting up a partial standing wave field on the left-hand side. And it transmits the remaining energy through to the right-hand side. So that model has been used many times by me, for one, and typically the outputs that are taken from the model are the proportions of reflected and transmitted energies, noting that those proportions don't depend on the incident energy because the model is linear. Another way of saying that is that the reflected and transmitted amplitudes are proportional to the incident amplitude. However, if we actually plot the solution around the flow, then we notice a problem with the model which comes from the small freeboard of the flow. So the problem is that for a phase of the motion, the wave field around the flow goes above the edges of the flow. There's nothing special about the parameters that I've chosen in this case. Although, if I'm absolutely honest, I should point out that the vertical scale is exaggerated here. It's a typical thing we do. And so that makes the problem look a little bit worse than it actually is. If I asked you what you would expect to happen in this sort of situation, I hope that you'd say that water is going to run onto the surface of the flow. And that's what we refer to as overwash. I'm going to show you plenty of lab experiments in which overwash occurs. However, the model only allows for the water to experience small perturbations away from its resting position, which eliminates overwash. In fact, you'll never get overwash with any sort of model based on a perturbation method. You can imagine that what the model sees are vertical barriers at the edges of the flow. In general, overwash occurs if there's some differential motion between the flow and the surrounding wave field. Obviously, the size of the differential necessary is relative to the incident amplitude and also to the freeboard of the flow. It doesn't necessarily only occur in the scattering regime, although all of the overwash properties that I'll show today are really only relevant for the scattering regime. So, two questions occur to me. The first is, does the presence of overwash affect wave propagation? In other words, does it affect reflection and transmission? I'm going to show you some evidence that it does. The second question is, does it affect the properties of the flows themselves? Now look, I'm not the person to answer that question. I don't have the necessary expertise, but it seems reasonable to assume that if you're forcing water onto the surface of a flow, then you'll affect the flow thermodynamically, at least. I remember someone during the first workshop talking about it being fashionable to give away the main results early during a talk. And I'm going to jump on that bandwagon right now. So what I'm going to show you are some results from a series of lab experiments that we conducted a few years ago at the University of Melbourne, in which we attempted to replicate the standard model that I showed you a few slides ago. What we did is we put a floating plastic plate into a wave flume, subjected it to regular instant waves, and then measured the transmitted wave field. On the right-hand side, you can see the transmitted amplitude as a function of the incident amplitude, where I've non-dimensionalized both with respect to the wave number k, which means you can think about them as being steepnesses. The black line is the prediction from the linear theory. It's a straight line because it's linear theory. The box and whiskers are the experimental data. When the instant amplitude is small, then the data are close to the theory. But as the instant amplitude gets larger, the data drift away from the theory. and note in particular that the data are always showing a smaller transmitted amplitude than in the theory. And we went on to show that this drop in transmission is connected to dissipation of wave energy as opposed to some sort of redistribution of the wave energy to different frequencies or different directions. Perhaps more importantly, we showed that if we remove the overwash by actually physically putting barriers on the edges of that plastic plate, then we got rid of that behaviour and the data is close to the theory for all of those instant amplitudes. And we've also gone on to confirm this behaviour with a CFD model. It's not the CFD model I'll talk about later. It's much cruder than the one I'll talk about later. In particular, we use quite a coarse mesh for the overwash, but we're still able to replicate this. What that says to me is that this behaviour is a bulk property of the overwash rather than depending on its finer details. So, the larger the instant amplitude, the larger the overwash, the greater the effect of the overwash on the surrounding wave field. So, even if overwash only occurs right at the very edge of the ice cover, where the wave amplitudes are largest, it can still have a significant impact on the wave energy that's able to penetrate deeper into the ice-covered ocean. This is where you begin to realise that Mike and I have been hanging around too much together. There's going to be about 3 slides which are almost identical to the ones he showed yesterday. It's a bit worrying that we didn't discuss this at all. Anyway, I'll say something different about it anyway. What I want to do is I want to take a step back now and I want to think about the properties of the overwash as opposed to the effect of the overwash on the surrounding wave field. The first lab experiments that we conducted were in a wave basin at the University of Plymouth. Again, we used a floating plastic plate and regular instant waves. We tested 2 plastics, one dense and rigid, the other lighter and more compliant, and we tested a range of thicknesses. For the waves, we tested 3 wavelengths and 4 different steepnesses. We found that overwash occurred in the majority of the tests that we conducted, and we noted 2 different types of overwash. The first was for gentle instant waves. In this case, overwash was only generated at the leading edge of the plate. The overwash it created was shallow and relatively slow. The most distinguishing feature of it is the presence of bores which propagate from the leading end to the trailing end. So bores are these sharp increases in depth. The black and white hole that you can see at the centre is a wave probe that we use to measure the depth of the overwash. But if we went to more energetic instant waves, then we found that the overwash was generated at both the leading and trailing ends of the plate. That led to bores propagating in opposing directions across the plate, and when those bores collided, they broke. The overwash is also deeper and faster in these cases. We then repeated the tests, but we replaced that wave probe with a motion tracking system in order to measure the motion of the plate. And we compared that measured motion to predictions from the linear theory. And we found that the linear theory actually does a really good job of predicting the plate motion. We did this in a formal modal sense. I'm going to show you some 3D movies, which are just a sort of nicer way to convey the agreement between the theory and the experiments. We're going to make use of the accuracy of the theory for the plate motion in our overwash model. Our overwash model is 2D, and it's based on a decomposition of the domain into an overwash domain, shown in green, the surrounding water, shown in blue, and the plate, which is the yellow. For the surrounding water and the plate, we use linear potential flow theory on the basis of the accuracy that I just showed for that theory in predicting the plate motion. For the overwash, we use nonlinear shallow water theory on the basis of those bores that we observed during the experiments. Now, we use the linear potential flow solution to force the shallow water equations. The dependent variables in the shallow water equations are the depth, that's the depth of the overwash, d, and the depth averaged horizontal velocity, which I'm calling u. We set the boundary conditions to be that the depth is equal to the height of the free surface from the surrounding water at the ends of the plate, above the plate, but only if the elevation is above the plate. If it's below, then we set it to be 0. And we do something analogous for the velocity as well. And we do all of this without any feedbacks from the overwash to the surrounding water, so that you can calculate the potential flow solution without any thought about the overwash at all. We then solve the shallow water equations numerically as an initial value problem, and we run it until we achieve a quasi-steady state. The movie that I'm going to show you here is an illustration of the good agreement that we get between the model and the experiments for gentle instant waves when overwash is only generated at the leading end of the plate. I want you to note in particular the agreement in the location and velocity of the bores. And we also get agreement in these cases for the overwash depth at the centre of the plate. The only real difference that you can see between theory and the experiments here are the shoulders in the experimental signals, and that comes from 3D effects, which obviously we don't include in our model. However, if we go to energetic instant waves, where overwash is generated at both ends of the plate, then the model isn't accurately recreating what we saw during the experiments. The problem is that in the model, when bores collide, they just pass through one another, as opposed to breaking as they do in the experiments. Well, it's to be expected because we haven't put any physics into the model to allow them to break. So then we quantified the agreement We did it in terms of the mean depth at the centre of the plate, which you can see on the left-hand side, and the deviation from the mean, which you can see on the right-hand side, both shown as functions of the instant wave properties. And this is just essentially confirming that the model is accurate for gentle instant waves with small instant amplitudes, which create shallow overwash, but increasingly overpredicts the depth and the deviation as the instant amplitude increases. And we then went on to show that the loss of agreement exactly correlates with the occurrence of bore collisions and breaking. But after all of this, still have the question, what are the validity limits of this model? All right, it clearly can't model breaking when bores collide. However, if we're interested in the effects of the overwash on the surrounding wave field, which I speculated earlier is a property of the bulk properties of the overwash rather than the fine details, then perhaps we don't actually need to model the breaking. And so the model could be valid for all of these instant waves that we tested. So the approach that we took to trying to ascertain the capabilities of our model was to apply it to the simplest problem that we could think of. And the problem that we chose is illustrated at the top of this slide. We have regular instant waves coming in from the left-hand side and interacting with the step, where the top of the step is level with the undisturbed surface of the water, so that the waves necessarily force overwash. Now, this problem is simpler because we have no freely floating body to deal with, and we also have only a single interface at which overwash can be generated, meaning no collisions between bores. We also want more measurements with which we can assess our model. In particular, we wanted measurements of the velocity field in addition to the depth, and we want those measurements at multiple locations. Because of that, we decided to compare to a CFD model rather than experiments. And it was at this point that we brought in Kevin Mackey to provide the CFD data for us. So Kevin's CFD model is based on the laminar two-flow incompressible Navier-Stokes equations, which are shown in orange at the top there. I don't want to talk about those because my lack of knowledge will be exposed very quickly. But I do want to point out that Kevin spent a long time testing the convergence of his model for this problem before he decided to run it on an unstructured mesh where the minimum cells were of the order of tenths of millimeters, and they were all clustered around the front of the step where the overwash is generated. Each 30-second simulation that he produced for us took 5 days to run on the 96-core cluster. But despite that, it's a really obvious thing to say, well, CFD isn't reality. So maybe by comparing to the CFD model, you're missing some physics. Well, fortunately, the problem that we're studying here is similar to models of the so-called green water phenomenon, in which large isolated waves force water onto ship decks. And that creates deeper, faster, shallow water flows than the ones that we look at in the overwash problem. Now, in the green water literature, it's been shown that CFD models similar to the one that we're using here are able to accurately replicate lab experimental models of the green water phenomenon, and for situations in which the Reynolds number is orders of magnitude greater than in the problem that we're looking at. So that gives us some confidence that if we were to go and conduct lab experiments on this problem, and we're not planning to do that, then the CFD would accurately replicate those experiments. I'm going to show you an example simulation produced by the CFD. I want you to concentrate on the blue, which is the water volume predicted by the CFD model. The green curve is the theoretical model prediction, and I'll describe that theoretical model on subsequent slides. I want you to note two things in particular. Firstly, when overwash is generated at the front of the step, then we get highly complex dynamics there, including overturning and air entrainment. Then later on, after the overwash is propagated along the step, I want you to note that it transitions to a shallow water flow, which is driven by bores. Now, if your eyes are very good and you can see the green curve properly, then what you see is that the theory isn't doing a very good job of predicting the CFD around the step front when the overwash is being generated. But we expect that. And despite that, we're going to go ahead and apply our domain decomposition method, in which we apply linear potential flow theory to the relatively deep water on the left-hand side and nonlinear shallow water theory to the overwash on the right-hand side. And I'll just point out that this model only takes 10 minutes to run on a bog standard laptop. Now, because the deep water problem on the left-hand side is so simple in this case, we can actually solve it analytically. And what we find is that the wave field is a combination of a right propagating incident wave with amplitude A and a leftward propagating reflected wave with amplitude R. And because by design, the deep water knows nothing about the overwash, then the deep water conserves energy. And that means that the reflected amplitude is equal to the incident amplitude. Well, there is one very interesting consequence of that. It means that we have a standing wave field in the deep water, and that means that the horizontal velocity is equal to 0. So then you think, well, how am I going to force overwash with this deep water with a velocity of 0? But we went ahead, ran the numerical model of the shallow water equations, and hey, we did generate overwash. And the reason that we're able to do that is contained in the characteristic plane, which I'm showing here. Now, taking a risk by showing this, I mean, depending on your perspective on these things, this is either a thing of beauty or a hideous mess. And I sit somewhere in between. But I'll point out the salient features. At the step front, x is equal to 0, over on the left-hand side there, we have only one characteristic entering the domain. That means that we get a hydraulic jump there. That means that our solution can be discontinuous there, and that allows mass and energy to propagate into the overwash despite u is equal to 0 being prescribed as a boundary condition. The other most striking feature of this characteristic plane are the shocks, which are the thick diagonal red lines, which emanate, well, they look like they emanate from x is equal to 0. Actually, it's a point very close to x is equal to 0. And we get one of those per period of forcing. And in the simulation, it's those shocks that give us the bores. I should also point out that this characteristic plane was calculated by post-processing the numerical solution. So what you're seeing here are two stills from the movie that I showed a couple of slides ago. One main difference is that got David to change the green curves to red curves, which I hope are easier to see. The still at the top is taken at an instant at which overwash is being generated. And it's really just confirming that the theoretical model prediction of the overwash at the step front is not doing a good job at all. The still at the bottom is a short time later when the overwash has propagated some way along the step, develops into shallow water flow with a bore. And now the theory is doing a good job. So the question is, how is it possible for the theoretical model to be able to predict that shallow water flow accurately along the step when it's doing such a poor job of predicting what's going on when the overwash is being forced? The figures on this slide are our explanation of this. What you're seeing here is on the top row, the mean mass flux, and on the bottom row, the mean energy flux as functions of instant amplitude and at 3 different points along the step. The predictions from the theoretical model are in black, and then there are 2 sets of data from the CFD model, one in which we applied no shear conditions on the step, which is similar to the underlying assumptions of the theoretical model, and then another one with a more standard no slip condition applied on the step. And all I really want you to take out of this is that the theory agrees with the CFD really well at all points, including at the step front where the overwash is being generated and we get the complex dynamics going on. Therefore, our conclusion is that although the theoretical model isn't able to predict the free surface at the step front when the overwash is being generated, I mean, it doesn't predict the overwash depth there, it is predicting the mass flux and energy flux at that point accurately, and that's allowing it to predict the shallow water flow farther along the step accurately. So for the last section of this talk, I want to go back to the effects of the overwash on the surrounding wave field, and to begin with at least, I'm going to stick with the step problem. The figure here is showing the free surface elevation time series at in the deep water 2 meters away from the step front. The linear theory is in black, the CFD model prediction is in red. So I want you to remember that in the deep water, the wave field is a combination of the instant wave and a reflected wave. And also recall that the linear theory doesn't know anything about the overwash. In particular, it doesn't know about mass and energy being pushed into the overwash. And because of that, it's going to over-predict reflection produced by the step. That's exactly what that figure is showing. And when we did some analysis of the CFD, we found that it was giving a reflection amplitude R, which is approximately 0.6 to 0.7 of the instant amplitude, as opposed to being equal to the instant amplitude in the linear theory. David has come up with what he describes as a two-step method for the reduced reflection. And again, I'm going to go back to a domain decomposition to try and explain this method. On the left-hand side, in the deep water, we again apply the linear theory, in which we have an instant wave with amplitude A and a reflected wave, but now with a reduced and as yet unknown amplitude curly r. On the right-hand side, we're again applying nonlinear shallow water theory for the overwash, and we're saying that the properties of the shallow water are those given to us by our model. So that's the first step in the method. In between those two regions, we're putting in there a transition region where something complicated is going on, which we can't solve exactly, but we know that it's dissipating energy. And we're going to assume that that transition region is sufficiently narrow that we can say that it actually has zero width, which means that we're treating it like a hydraulic jump. And we then perform an energy balance over the composite domain between x is equal to xl and xr, and we assume that the solution is periodic. And what we do is we derive an expression which involves the energy loss in the transition and also the energy loss due to bores in the shallow water. But we're only really interested in the energy loss in the transition at this point. And so what we do is we shrink down that shallow water region to a point as well, and that gets rid of the energy loss due to the bores. We then sub in our expressions for the wave fields, and we end up deriving this equation which we can solve as a cubic for the reduced reflected amplitude curly r. And note that if there's no overwash, then we end up with r is equal to a, so we're back to the linear theory. And this method does an amazingly good job of predicting the reduced reflection. Really amazing. Couldn't believe it when I saw it. The figure at the top is that time series from a couple of slides ago, but now with the two-step method replacing the linear theory. Perfect agreement. The figure at the bottom is the reflected amplitude as a function of the instant amplitude, comparing the two-step method and CFD model, and with the linear theory there just as a reference. Again, almost perfect agreement. Apart from writing up his thesis, David is currently working on extending that two-step method to the floating plate problem. It's a more difficult problem, so we need some additional assumptions. The first thing we assume is that there are no feedbacks, by which I mean that once wave energy goes into the overwash, then it never returns to the surrounding wave field. The second assumption is that the reflected wave is unaffected by the overwash. So what I should have said is that he's extending the method for transmission by a floating plate. What we observed in the experiments that I showed you earlier in this talk from analysis of the reflected field there is that there's very little effect of the overwash on the reflection. This is a very different problem to the step problem in this respect, because the floating plate only very weakly reflects the instant waves. The figure at the bottom is just a preliminary figure, and it's basically the same thing, that you saw earlier during the talk. It's the transmitted amplitude as a function of the incident amplitude. The black is the linear theory. The red is experimental data. But now, rather than showing you the boxes and whiskers, I'm just showing you the median values. The blue are preliminary results for the two-step method. And again, it's just fantastic agreement. Okay, I'm running out of time, so just a couple of things to say from this concluding slide. The first one really echoes something that Mike was saying yesterday. Look, at the end of all this, what are we able to do? I'm going to say that we are almost able to predict what goes on in a wave basin in Plymouth or Melbourne when you put a plastic plate in there and subject it to regular incident waves. It was a tough problem, it was a lot of fun, we learned something from it. But the question is now, can we translate it to something real, something involving sea ice? Well, I think in the first instance what we really need is some evidence that overwash is going to be of some importance for the sea ice problem. I have some belief that it will be, but we need someone to actually be interested enough to go out there and provide some data on that. It's a really difficult thing to do. We do have some lab experiments coming up next year in a proper ice tank, so that'll be a step in that direction, and I have had some interest from some sea ice people in this problem, but really to look at the effect of waves putting water onto the surface of floes as opposed to looking at the properties of the overwash or the properties of the surrounding wave field. I think I'll leave it there so I have some time for questions.
Thanks very much, Prof. Are there any questions, John?
Yeah, I do want to comment on this second point you have put up here, the lab experiments. So I have experience on this, and I've done an experiment which is almost spot on this. Your matching region is actually the condition, the edge condition of your flow or your plate. That is the matching condition. So in my experiment, I rounded it off. And you always know that linear theory works. You can go down, down, down in the amplitude. You can have like 0.5 millimeter.
Sure.
And then you would model experimentally or theoretically an incoming wave with a flux. And you can have zero reflection.
Zero
Zero
reflection.
There's zero reflection. You don't have any standing wave. You play with a very tiny. So if you want to have, So I can show you these results.
With a thin floating plate.
I had a box, fixed box like.
Broadband in frequency. Or?
No, I had just one frequency. It's a function of the frequency, but you can have frequencies which are completely transparent. The point is that you accept for a small. You have a standing wave plus a flux, and the flux corrects everything. So what you do, the condition you have at the end, at the start of your ice flow, that dictates everything. So that is a matching condition, and so you have to be very careful what you assume there, because that dictates everything.
Yeah, I somewhat disagree with you on that. I would have agreed with you before we actually went ahead and investigated this model, but it seems that you can get the boundary condition wrong, and the shallow water doesn't care that much about it. It's robust to that. We know that we're getting the flow.
And you can define a linear regime because you can go down in the amplitude, and you have a perfect linear regime, and you have like an incoming wave with a small flux, and that flux determines everything.
Can I suggest that you...
Yeah, okay. So I misunderstood what you said originally.
I think you're clever one or maybe two, but very quick questions, please, because we're almost done.
When you solve the nonlinear shallow water equations over the plate, do you take into account the moving orientation of the plate?
No. I mean, yeah, I should have said that, but we did actually do some calculations to work out that the acceleration of the plate is so small that the effect is negligible, and it's such a computational burden to try and put something like that in there that we just thought, well, we'll wait to see whether there's evidence that we need it in there. That's a good question.
Two more quick questions to Ben.
Thank you. My question is really just a general question of when you go back, I mean, the theme of the conference, of course, is mathematics of sea ice phenomenon. And I'm interested in how often you think that the overwash will be an important phenomenon in the marginal ice side. And I ask that question really based on experiments that I have actually personally carried out during the MISEX program in the 80s and 90s, where we landed helicopters on ice floes in the marginal ice zone, and needless to say, helicopter pilots don't like landing on top of floes which are underwater. So we must have done those experiments on relatively dry ice floes. They were quite close to the edge, and they were done in a range of oceanographic conditions. So the question is how often, really? And do you think it's going to get worse?
I mean, I can't just say often, not often in response to that. I mean, what I said earlier was that it depends on the differential between the motion of the surrounding wave field and the flow itself. And that depends on a variety of parameters. You know, if you're landing on a really large flow, then
20 metres.
How high was the wave amplitude?
Oh, a metre.
I think we better. I think we better call today. We're way past time already. Thank you. Thank you very much.